Hello students, this is Mr. McAllen, and today we're going to be talking about complex zeros and the fundamental theorem of algebra. Well, basically the fundamental theorem of algebra says that whatever the degree of your polynomial is, it guarantees you that same number of roots. Now those roots can be real, or they can be imaginary, or they can be complex. That's what the fundamental theorem of algebra guarantees you. It says that you will turn a polynomial into, if you factor it, or if you try to solve for the roots, you should find as many roots, whether they be real or imaginary or complex, as the degree of the polynomial. So what we're going to do is we're going to go through a couple examples of how you can build some polynomials from different linear terms which have embedded in them different root values. So look at the objectives. So we're going to discuss other types of roots. The roots we have been finding so far to date have all been real roots. These roots have been rational. On the quiz we just took, you notice that two of the roots that we were finding after we found the two rational roots, they happen to be irrational roots, which are still real, but they're not going to be found using our rational root theorem. Today, in this video, we're going to look at when we have complex roots or complex zeros. You'll see that term used synonymously. And we're going to also discuss possibly some irrational roots. So let's look at our first example. First example is just a simple quadratic. Now we're not going to do anything really crazy with this. All I have planned for this problem is I first plotted it to show you on Desmos that that if you plot the polynomial x squared plus 2x plus 5, I just want to show that the quadratic or the parabola is not going to cross the x-axis. As you can see, you can see the x-axis, the curve is well above the x-axis. There won't be any crossings of the x-axis, and as a result, you can conclude that any sort of roots that we would have with this polynomial would be imaginary roots, or they would be non-real roots. So crossings of the x-axis, where they cross, dictate a real root, and those roots could be rational or irrational. So let's go back to if you took this function and you use a quadratic formula just to verify what I said, remember you have the a term is equal to 1, the b term is equal to 2, and the c term is equal to 5, and you work through the quadratic equation of minus b plus or minus the square root of b squared minus 4ac all over 2a. This gives you your two root values. So this would be minus 2 plus or minus the square root of negative 2, I'm sorry, that would be 2 squared minus 4 times the a and the c value would be 5. So we have all over 2. So what we end up getting is negative 2 plus or minus root of negative 16 all over 2. And then the final result is we have negative 2 plus or minus, we would call this 4i, because the negative under the radical is an I and root of 16 is 4. The final result is going to be negative 1 plus or minus 2i. So our two root values, x1 is equal to negative 1 plus 2i, and our second root is equal to negative 1 minus 2i. I want to just note something about this. These two roots, complex or these are complex roots, but roots typically come in conjugate form. So you can see that this root and this root are conjugates of each other, and it's necessary that they are conjugates of each other so that when you multiply them out, if you were trying to construct the polynomial, you would get all your coefficients would be real numbers. That you wouldn't have any, well, not real numbers, or rational numbers, because you can't have any coefficients that are not rational. Irrational coefficients won't lead to a polynomial. So let's look at our next example. And in this example, they say to write the function, polynomial function, in standard form, identify the zeros of the function and the x-intercepts of its graph. So well, we can clearly tell that for the first, let's do the last part first, the x-intercepts for a. the x-intercepts are not going to exist, because if you set that equal to 0, you're going to x equals 2i, and from the other one you're going to get x equals to negative 2i, so you're not going to have any crossings of the x-axis. You can see that these roots are clearly imaginary, and as a result we won't have any crossings. But if we were to FOIL it out, and if we were to put it in standard form, foiling this polynomial out, you would get x squared minus 2ix plus 2ix minus 4i squared. And as a result, because these terms cancel, you'll get x squared, and I squared is negative 1. You get x squared plus 4 as our polynomial in standard form. On the next one, I suggest if you were to do this problem, you can clearly state what the roots are by setting the linear terms equal to 0. So for part B, the x-intercepts, there's only going to be one intercept, and that's going to be at x equals 5, because the other two are going to be imaginary. And I would suggest that if you're going to put this in standard form, you first FOIL out the conjugate roots, and if you do that first, you're going to have x minus 5 out in front, and then you're going to have, when you FOIL this, you're going to end up getting x squared. The inner is going to counteract with the outer, and so you're not going to have any inner term, and the last times the last is going to give you minus 2, because root 2 times root 2 is going to be 2i squared, so it's really going to look like x minus 5 times x squared plus 2. So then you would FOIL this to get your final polynomial. You would have x cubed as your first times your first, minus 5x squared. Then you would have plus 2x, and your last one would be minus 10. So this would be your polynomial for part B in standard form. I may ask in the form for you guys to FOIL out or put in standard form part C, so make sure you pay attention to the form tonight, or whenever you do this. So the last type of problem I want to show you how to do is what happens if we give you we give you roots of a polynomial, and we say find the polynomial function of minimum degree. With these, they have to have real coefficients, whose zeros include -3, 4, and 2 minus I. So this is kind of a trick question, because at this point you're supposed to notice that that's a complex root, and if you have a complex root, in order to make a polynomial, you need its complex conjugate to be in there as well. Let me just check to see how we're doing that time. Okay, so in order to construct this polynomial of minimum degree, I can't have a third degree polynomial, because if I try to multiply these linear terms out, so for the linear terms would be x plus 3, x minus 4, because remember, these are the roots, and the linear terms are such that when you set it equal to 0, you get, when you set the linear terms equal to 0, you get these root values. And I have, let me just make sure the microphone's working. Yeah, we're still good. Okay, so now we have the two other roots. We have x minus 2 minus I, and we have x minus 2 plus I. So when we are working with these polynomials, we would like to first multiply this out. And when you multiply this out, because you want to get, if we multiply the roots with the complex conjugates out first, we're going to get rid of the I terms. It's going to make life a lot easier for us. So, but just beware, because you have actually 3 terms being multiplied by 3 terms, which will give you 9. So I have x minus 2 plus I when I distribute the negative, and I have x minus 2 minus I. And when we do that, you just have to be very careful when you multiply it. I always use, when I engage in multiplying 3 terms by 3 terms, I use the box method. A lot of people are not they don't favor this method, so I'm just doing it because it's visual. It's easy to keep track of terms, so I'm going to just show you how I write it out, and then I'll pause the video so you don't have to see me work through it, but then you know, you'll see how I collect terms. So I'm just going to pause the video and I'll be right back. Okay, so I'm back, and you can see I multiplied through in the box. So now what I'm going to do is I'm going to, if you look at the diagonals, you can see the diagonal terms kind of are related to each other. So here I have x squared minus 4x, and I have plus 4. But then if you look, the I terms here and here cancel, the negative 2i and the positive 2i cancel, and the last term is negative I squared, which makes negative of negative 1, which means plus 1. So my polynomial that I get from multiplying these two roots is x squared minus 4x plus 5. So now I'm going to take that polynomial, and remember I've got like x plus 3 times x minus 4 times x squared minus 4x plus 5. So now what I'm going to do is I'm going to FOIL this one out, and I've got x squared minus x minus 12 when I FOIL that out, and I'm going to multiply by x squared minus 4x plus 5. So in this case I can also do a box method if you want. If not, you can do it the way you want to do it, where you keep track of terms. But remember, you're going to have 9 terms. You're going to have 9 terms, so minus x minus 12, and I have x squared minus 4x plus 5, and I'm just going to x to the 4th minus x cubed minus 12x. And then next row I'm going to have negative 4x cubed. I have plus 4x squared, and I have plus 48 x. Right, this should be x squared here. And then I have 5x squared, I have negative 5x, and I have negative 60. So I'm just going to pause it and double check and not waste your time. Right, so I'm back, and I double checked my work just to make sure, so I'm pretty confident that I'm okay. So we've got x to the 4th, you have minus 5x cubed, you have minus 3x squared. And the thing I like about the box method is it helps me organize, because on the diagonals are all my terms. So here I have plus 43x, and then I have minus 60. So this would be my final polynomial of lowest degree that would have these roots. And remember, I had to add one, because if I didn't add that root, I would have had imaginary numbers in my coefficients. So polynomial is done. Hopefully you understand. You know, whenever I give you a list of roots, you always have to look at the roots. If you have imaginary or irrational, you've got to have the kind of the conjugate pair. So for example, in summary, if I gave you you know, these are roots, right? So here we have in example 3. We're not going to do this problem, but if I gave you this problem and I said write a polynomial function of minimum degree in standard form with real coefficients whose zeros include, so here that's okay and that's okay, so that's just x minus 1, a double root. And then here on this one, I would need to also have, I would have x minus 1 plus 2i, and I would need to multiply that by, or have another root to pair up with it, of x minus 1 minus 2i. And then for the last one, I would need a pair of roots. I would need x minus 1 minus I, and then another term, x minus 1 plus I. So remember to always look at the roots and figure out if you need to pair up the roots, so that you make sure if you multiplied out the whole polynomial, you would be able to find a polynomial so that you did not have any anything but real coefficients. Hope this video has helped, and we're going to practice more problems on these on Monday, and look forward